let's start with a group. Okay, so suppose we have a G group and we want to construct a corresponding Eilenberg-MacLane space. So the idea is simply you attach cells which will kill higher homotopy, but that needs one technical result, but we already did the work needed for that, which is that, so suppose we have X a CW complex and X0 is a point in it, so X0 in X. Then if I look at pi n of the n skeleton, this surjects onto pi n of the whole space. We'll need this because we are going to be destroying a lot of homotopy. We want to know that we don't accidentally create homotopy. And the proof is that, well, we have a map. So suppose, so let theta be a map which maps 0, 1, n, and it's relative to the boundary of it. Okay, as usual, to x0. Then I want to say that it's homotopic to a map here. Okay, then up to homotopy, first of all, theta intersects interiors of only finitely many cells. So if you recall, this is what we did by claiming that compactness. So we showed this for a general compact space, that because the set of midpoints is discrete, the image can hit only finitely many midpoints, and then we just push out from the midpoints to achieve this. And also because this is n-dimensional disk relative to its boundary, which is already mapping into, so let's say it belongs to the 0 skeleton. Okay, we can take x0 to be one of the vertices in the cell decomposition. Okay, so then the boundary already belongs to the 0 skeleton. We'll say n is at least 2. This will also be true for 1. We have to be a bit careful about the non-abelian nature, that's all. But so theta intersects interiors of only finitely many cells. And now, so theta has image disjoint from, earlier I had called this k and that n, so let's call it m cells for m greater than n. Okay, disjoint from the interior. Okay, this was the proof that involved linearizing and so on, but the latter statement is simply saying that theta has image in xn, which is all that is required. So up to homotopy, and this is all up to homotopy fixing the boundary. We have these things. So this tells you this surjects. Okay, so now we can construct. So the construction, now we are set. Okay, so construct x2 such that pi 1 of x2 with respect to x0 is g, and let's say x0 belongs to the 0 skeleton. We have done this earlier. Let's just recall what we did. We wrote G with a presentation, that is a bunch of generators and a bunch of relations. We took a free group on those generators by making a graph, and then we killed those relations by adding 2 cells. Okay, now take generators. So take generators, there could be infinitely many, of pi 2 of x2 with the favorite base point. Okay, so let's call them, okay, so let's call them theta alpha and alpha in A2. Okay, these give, so these are maps. So what are these theta alpha? So we are in x2 now. We are going to be looking at generators of pi 2. So these are going to be maps from the disk. So the theta alpha. So theta alpha are going to map 0, 1 squared to, but relative to boundary of 0, 1 squared to x2 and x0. So these give maps V alpha mapping S2 to the space x2, and indeed the special base point of x2 to the point x0. Okay, so now we attached 3 cells on these. Okay, so now when we attach a 3 cell along this, if I have a specific map from S2 and that map bounds a 3 cell, then the corresponding homotopy theta alpha extends to a homotopy from this to the identity. Given theta alpha, you get a homotopy from this to the identity. We proved this when we assumed everything was all maps extend is being equivalent to the homotopy group vanishing, but a specific map extending is for exactly the same reason, equivalent to the specific map being trivial in the homotopy group. Okay, so we attach 3 cells along this. Now we are done. So then pi 2 of x3 x0 is trivial. Why is that? Because we see all these generators theta alpha now become trivial because of the cells we have attached, but by the theorem above, no new generators have been created. So x2 surjects, but every element in x2 is now by construction trivial, and hence the whole pi 2 is trivial. Okay, so we have by constructed a 3 complex x3 with pi 2 trivial. Okay, similarly, so given xn with pi k of xn x0 being trivial for 2 is less than or equal to k and is strictly less than n. Okay, we construct xn with xn plus 1 by adding n plus 1 cells with pi k now of xn x0 is 0 for all k, with 2 is less than or equal to k is strictly less than n plus 1, that is we include n in these things, and then let's just say take limit. So we have attached cells in such a way that we are killing higher and higher homotopy groups. Okay, so the only thing we knew is that when you attach a high enough dimensional cell, we can kill, that is clear by construction, but we don't accidentally also create homotopy. So given any group, we have an Eilenberg-MacLane space attached to it. Often these spaces are much nicer. We saw that they could be as nice as the torus or the circle. Okay. And there are other interesting examples as well. But here we have established this portion of Whitehead's theory. So we have understand how we can reverse algebraic topology and say algebraic data determines spaces and maps completely in special cases. In special cases where the spaces are nice enough, they are CW complexes, but also there is homotopy only in one dimension. Okay, now Whitehead's results go well beyond this, but as far as this course is concerned, this was meant. This is all we will see. It was meant to illustrate some of the techniques, okay, and crucially, one bit of geometric topology.